Good morning, class, and welcome to week 5, I believe it is now, into the online semester at the University of Kurdistan. Last week we talked about concrete, we talked about how you make it, the key ingredients, the basics of it, how you mix it and batch it, and the importance of curing. This week we're going to talk about the properties of hardened concrete. Concrete which has set, it's become solid, and and key properties of those concretes, and how we then assess it and test it and know if the concrete is suitable for the application in our civil engineering infrastructure. So in this lecture you're going to be learning about some of the key properties of hardened concrete. So solid, hardened, solidified concrete that's gone strong. We're not talking about properties such as properties such as slump or workability. Those are properties of wet concrete. We're going to also talk about how those properties are tested, the key factors that influence these properties, so how we can improve the properties. And we're also going to talk about certain kinds of concrete which are special in some cases. So the key properties we're going to be looking at are shrinkage, modulus of elasticity, which we touched on when we did aggregate, durability, creep, and strength. And with concrete, it's usually compressive strength that we are most interested in. So let's get away now with strength. This is by far the most important property for concrete usually, and usually we're measuring compressive strength for concrete. So remember, strength can be measured in different directions. You can measure it in compression, where the material is being squeezed. It could be tension, where it's being pulled apart. It could be shear, where the forces are opposing one another, like compression, but they're on two different planes, so there's almost a tearing motion. And flexural testing, that's actually where we're looking at a beam, and there is a load in the center of the beam, and it has two supports. And you can see in that beam, as that load comes down, the top of the beam is actually in compression, and the bottom of the beam is actually in tension. So part of the beam is being pushed together, and part of it is being pulled apart. Now, generally with concrete, for most concretes, they have very good compressive strength, but are quite considerably weaker in tensile strength and shear strength. So if you were going to have a concrete beam and you were going to apply a flexural load, where would the beam crack? Would it crack on top of the beam, or would it crack at the bottom? Well, it would crack at the bottom first, wouldn't it? Because that's the part which is in tension, and the concrete is weakest in tension. Now, when you have a concrete, remember a concrete is a composite material. It's made up of aggregate and cement holding the aggregate together. What you need to know is that it will break at the weakest element, and cement is usually weaker than the aggregate. So when we're choosing an aggregate for concrete, we're not normally interested in the strength of that aggregate, although it does need to be stronger than cement. The reason for that is the concrete will break when the cement breaks. The strength of the cement and not the strength of the aggregate determines the strength of the concrete. Look at it this way: if you had a concrete that was made up of an aggregate which had a 200 megapascal compressive strength, and it was held together with a cement which had an 80 megapascal compressive strength, when would the concrete break? Well, it would break under a load of 80 megapascals. It will break when the cement breaks. So how do we test strength? Well, you've probably seen some of these machines before when we did the tour of the lab back in week 1. We will do all of these tests, I hope, when we get back to the university. But you can probably tell here that the test in the top right corner, that is testing compression. You can put a concrete sample between those two steel plates, and a hydraulic jack will slowly squeeze the concrete until it breaks. Likewise, the one on the top left-hand corner, you can place a sample, and this doesn't need to be concrete. It could be any sample. It could be steel or plastic. And you place it in the center there, and it's being pulled apart until it snaps. That's tensile strength. For concrete, it'll be a lot weaker than the compressive strength. The bottom left-hand corner, you can probably see there if you zoom in, that this is actually testing flexural strength. It's testing the strength of a beam. You've got a jack that pushes down a load in the center of the beam that's resting on two supports that are set apart. And then this machine on the right-hand corner, this is used for measuring shear strength. You can actually see how there's two jacks on that little black box. We would fill that black box with our material, and then we would actually apply two forces to it in opposing directions, but on different planes. And we will see how long it takes before the material tears and breaks in shear strength. So let's start with talking about testing compressive strength for a concrete. Well, first you're going to have to make a concrete sample, and normally for most concrete labs we would be testing concrete using cubic samples, similar to those blocks that you can see on the right. You can also make cylindrical samples, but normally for normal concrete it's a cubic sample. Now remember that when you're measuring strength, that is measured in pascals, or usually in the case of concrete, megapascals. And the SI unit for a pascal is 1 Newton per meter squared. It is a force over an area. So remember the FC here, that's actually a measure of a pressure, the compressive strength. P is the pressure that's being applied, and A is the cross-sectional area of the sample. So the area that the force is being applied to. So in the case of a standard cubical sample, like the photo, that will be 150 millimeters times 150 millimeters. Remember, you've got to keep it in SI units, so it would be 0.15 meters times 0.15 meters. And that will give you the strength in pascals. It's going to be a very large number, so that's why we normally measure concrete in megapascals to the power of 6. Now, when we're squeezing the sample in the compressive strength tester, you can see there that actually there's a cylinder sample being tested, not a cubic. The machine will slowly increase the force, the pressure that it's squeezing the sample at. And it's quite slow. It's usually 0.2 megapascals per second. You don't want it to be high speed because you might end up with a dynamic loss, which means that if you're throwing force at it at a high rate, parts will chip off quickly, and and you'll end up be measuring brittleness rather than strength. So with normal concrete, the test can take about 5 minutes, and you will see on the screen, not with our machine because we've got a cheap machine, but normally what you're trying to measure is compression's strength against strain. So strength is basically the pressure it can withhold, the force over the cross-sectional area, and you will be measuring that against strain. So strain, you should have learnt about this when you did physics, and what this is basically looking at the percentage change in the cross-sectional area. We talked a little bit about this when we did aggregates, but you're looking at if the sample is 100 millimeters in height and you squeeze it, and it changes the height down to 99 millimeters, well, that's going to be a 1% strain, or a 0.01 strain. It's usually given as that, and there's no ratio, there's no unit, because strain, of course, is a ratio. Now, normally with concrete, it's not very squeezable. It's not very spongy. The strain will be about 0.0005 at most. That would be a spongy concrete. You can squeeze it. But anyway, as you're adding pressure, there will be a small deformation of the concrete where it starts squeezing. And that's why you can see a curve with those lines forming. And then it will start turning down and moving down. So that will mean that the force is decreasing. And that's because basically cracking has started. So what we're trying to measure is not the ultimate strength where basically it disintegrates, but the top of that curve, the maximum force it can actually withhold. That gives us the maximum strength of the concrete. So that is measured at the peak of the stress-strain curve. Now, when you do this test, you should probably do it several times. The standard is actually you do it at least 12 times with 12 different samples of the same concrete, because concrete is not always consistent. You might have a little bit of some strong concrete, some weaker concrete, and what you need to do is you need to make sure that there's no large discrepancy between the concretes. If there is, that means it probably wasn't mixed well properly or not cured correctly, evenly, and you need to do the sampling again. So there are a lot of different things that can affect the compressive strength. Now, one of the ones which we already talked about was curing. So basically, the longer you cure your concrete, that will mean the longer the time that the cement molecules will have access to water to react with and form those strong hydraulic bonds in your hydraulic cement. Now, that's very important. That's probably one of the biggest factors where people design a concrete. They suspect it's going to be, they assume the concrete has enough strength, and then after they build the concrete, it doesn't reach the strength that is required. It's usually down to curing. That is the biggest mistake people make. They don't cure the concrete correctly or for long enough. Now, equally, the hydration rate has an effect on the compressive strength. There are some cements that react very quickly with water and others which take a long time. Now, that's important because if it reacts very slowly, potentially the water will evaporate in that time, especially if you haven't cured it correctly. And that will mean that the cement molecules won't have water to react with. So hydration rate is tied with curing. If it's got a slow hydration rate, then you need to cure for longer to make sure that there is water in contact with the cement molecules. Now, heat of hydration, remember that's different to hydration rate. Hydration rate is about how fast the reaction takes place. Heat of hydration is all about how much heat comes off the exothermic reaction when cement reacts with water. Well, if you have a high heat of hydration, that can be a big problem too, because if you have a high heat of hydration, that heat will actually burn off and evaporate a lot of the water, which is needed to react with other cement molecules. So you've got to manage that heat of hydration. The other thing is void ratio from lack of compaction. This can actually cause big air pockets to be inside the concrete that give no strength to the concrete. A high void ratio means a low compressive strength. Equally, the void ratio is influenced with the type of cement you're using. If the cement has a lot of air particles that come off the reaction, then those air particles are going to be trapped inside the concrete. Remember, concrete, if you look at it through a microscope, it will look a little bit like Swiss cheese, where there's been all these channels formed as air escapes the concrete. And you want to keep that to a minimum for a high strength concrete. Now, the amount of cement is very important. Now, it's not necessarily just the case that the more cement you use, the stronger the concrete will be. Obviously, if you don't have enough cement, you're not going to have all of the aggregate particles binding together, and that's an opportunity for the concrete to break. It would weaken the concrete. But if you have a very high cement to aggregate ratio, that means all of the aggregates are not going to sit on top of one another, and you're going to have large pockets of the concrete, which are basically just cement water paste which has dried. Now remember what I said, cement is weaker than the aggregate. So if you have a high amount of cement where that is holding the aggregate particles apart, that is where the concrete will break. So the amount of cement is very important. If you have too little cement, it will make the concrete weaker. If you have too much cement, it will make the concrete weaker. What you need is enough cement that it fills the voids between the aggregate if they were sitting well compacted, all the aggregate particles. The type of cement can influence the compressive strength too. Remember what I said, that lime and gypsum, or also okay, no, we didn't cover that cement, but lime and gypsum, they tend to be weaker cements than, say, Portland cement. And that's the main reason why we use Portland cement rather than lime these days, is because we need high strength applications for our concrete. The water and cement ratio, this could be anywhere between cement to water ratio could be anywhere between 0.6 1 to 0.6 to 1 to 0.35. Now remember, you need water to react with the cement, and it's about 1 to 0.35 for every cubic meter or kilogram, of cement. You will need about 350 grams of water for the hydraulic reaction in Portland cement. However, in reality, you need more water than that, so you have workability, so you have some slump, so you can place and mix the concrete and transport it through pipelines. Now, that excess water will eventually evaporate and leave voids in the concrete, weakening the concrete. However, that excess water also gives workability to the concrete. And so that's one of the big issues with making concrete. Do you have a high, determining the water cement ratio? If you have more water, you will have more workability. If you have less water, you will have more strength. So you need both in a concrete, and so it's a balancing act. And that's one of the key things that goes into designing a concrete mix. And finally, durability. If the concrete is chipped or cracked or damaged, then it's going to lower the strength. And we're going to talk about things which can cause that damage in this lecture as well. So just remember, the concrete compressive strength is one of the key parameters in the design and evaluation of concrete. This is a collapsed bridge pier, and you can see that it's failed in compression. It's been squeezed and it's broken. Now, the reason why that bridge pier failed was there was damage to it. There was a large crack in the concrete, which actually had been caused by a car driving into it. But then, because the construction engineer hadn't put enough cement in the concrete, and a lot of the aggregate, particularly fine aggregate, was sitting loose, that little crack pushed it over the threshold, and then you had a compressive strength failure where the whole beam, the whole pier just squeezed together and the bridge collapsed. And there's no way of fixing that. They had to actually tear down the entire bridge and start again. It cost many millions of dollars, and I suspect some construction engineer or design engineer was sued for this. So now that we've looked at strength, let's look at the other side of that equation, which is modulus of elasticity. You may have heard of this called Young's modulus too. You may have heard it as Young's modulus if you studied this in physics. But remember, we had that curve, the stress-strain curve, with stress on the y-axis and strain on the x-axis. Well, Young's modulus is really about trying to determine how stretchy a concrete is if we're measuring tensile load, or how squishy it is if we're measuring compression load. So you can see there the picture of three different, well, they're all the same sample, but they're being squeezed with compressive force. And as they're being squeezed, they begin to deform, they change shape. Now, that might be easy to picture with a rubber ball or maybe a plastic dice. But what you may not realize is that concrete also deforms when placed under a load. Ever so slightly. It's not a lot of deformation. You can't see it with the naked eye, in fact. But there is deformation. And there's two kinds of deformation. There's elastic deformation. That means that when you take the load off, the concrete or the sample, it will bounce back to its original shape. So just like a rubber band, how you stretch it and then you let go, it will bounce back to its original shape. And then if you keep applying force, you will lead to plastic deformation. This is where it will become deformed permanently. Now, normally with concrete, this will be in the form of cracks that don't suddenly repair themselves the moment you take the force off. So with concrete, we're talking almost always about elastic deformation. Now, this could be measured in compression or tensile or shear or even flexural directions. But remember, the modulus of elasticity could be different depending on what force is being applied. Just as concrete has a different compression strength to its tensile strength, so it will have a different modulus of elasticity for its compression direction as opposed to its tensile direction. So how do we measure the modulus of elasticity? Well, the modulus of elasticity is basically the gradient of the stress-strain curve. And this is done when the concrete is elastic, so it's the straight line at the beginning of that curve. Now, it's basically a measure of stress, which is measured in megapascals, over strain, which is just a ratio. It has no unit. Stress over strain gives you the modulus of elasticity. So the higher the modulus of elasticity, that means that that line between the stress-strain curve will be steeper. It will have a steeper gradient. And the higher the modulus of elasticity, that will mean that the concrete is stiff. Now, if it's a very low modulus of elasticity, the gradient of that line will be shallow. It will be a shallow incline. And it will mean that the concrete is not stiff. It has a lot more flex to it. It's more flexible. Now, what determines the modulus of elasticity in a concrete? Well, it actually comes down to aggregate and cement ratios. Remember, cement is weaker than aggregate. Likewise, cement actually has more flexibility than aggregate. It's more squeezable. And so if you have a high aggregate to cement ratio, you're going to have a higher modulus of elasticity. The concrete is going to be stiffer. Also, the shape of the aggregate can affect the modulus. If the aggregate shape is very elongated or flexible, then you're going to have large pockets, which is made up of cement water paste, which is more squeezable. So if you have flaky aggregate, that will actually decrease the modulus of elasticity. It will make the concrete more elastic. Now, why do we care about modulus of elasticity? Well, if you have a concrete that has a very high modulus of elasticity, it will mean that it will crack in extreme events. I don't know if you remember, but back in November 2017, we had an earthquake here in Erbil. Now, I was in my apartment, which is on the 8th floor of a high-rise apartment building. So when the earthquake hit us, we actually had the sensation that the building was swaying. It was rocking backwards and forwards. Now, that was actually by design. If you had a concrete that had a very high modulus of elasticity, the concrete would have cracked instantly as soon as the earthquake hit, and the building would have collapsed. Instead, it had some elasticity, and the building swayed, and that was able to dissipate a lot of the energy from the earthquake. Modulus of elasticity is of extreme importance for designing buildings when the building needs to withhold an earthquake. Now, if the modulus is too low, that means the building is going to be too flexible. Components of the infrastructure will not align. There will be sagging of beams and other things. Remember, we're trying to design civil engineering infrastructure. And in civil engineering, we're trying to design things that don't move, or at least they shouldn't move. So, finally, modulus of elasticity is a measure of stress over strain. Strain is unitless. It has no unit. It's a ratio. Stress, on the other hand, is a force. It's measured in megapascals. And normally with concrete, you're going to have a pressure of anywhere between 40 to 120 megapascals. The strain will be very small. It'll be around 0.005. So that means the modulus of elasticity for concrete could be anywhere between 10 to 50 GPa, gigapascals. That's how we measure elasticity. But typically for most civil engineering infrastructure, we want the modulus of elasticity to be around 20 to 30 gigapascals. If it's lower than that, it's too flexible. If it's higher than that, it's too stiff. And we'll talk about what happens if it's too flexible in a moment when we talk about creep. But how do we measure that gradient? Well, it should be easy if we have a perfectly straight line. However, because of implications in the testing apparatus of the machines for testing compressive strength or tensile strength, that line could actually be a little bit wavy, or it could even bounce up and down with noise. That's just an oddity with trying to measure very exact forces on a material which is variable. So the standard way, according to the ASTM, American Standards and Trademarks, C469, the standard way of measuring the modulus of elasticity for concrete is this, where sigma 2, that is 40% of the ultimate load, meaning what is the maximum strength of the concrete where it was at 40% of that, and EGMA 1, that is the strain at 0.00005. We're talking a very small strain here. And then EGMA 1 is the strain when sigma 1 is the force. And EGMA 2 is the strain when sigma 1 is the stress, and sigma 1 is the stress when EGMA 1 is the strain. And then the formula we use is this: E, which is the symbol for Young's modulus or modulus of elasticity, equals sigma 2 minus sigma 1 over EGMA 2 minus EGMA 1. Now, just so you know, you don't need to remember formulas. Any formulas that you need will be given to you in the exam. I can't remember formulas. Every time I need to work out moduluses like this, I have to go online and check out what the formula is. But you should be able to use that formula. It's a very easy formula. So from that, you should be able to work out what Young's modulus is. And this gives you basically a very general but quite specific at the same time measure of what the gradient is on the stress-strain curve. I now want to talk to you about creep. So that picture on the right there, that's Tom York. He's the lead singer of a rock band from the UK called Radiohead. Back in the 1990s, they had a big hit song called Creep. You may have heard it. Well, this is a different kind of creep. Creep is basically what happens to concrete when the concrete has a modulus of elasticity which is too low. Basically, the concrete is changing its shape because it is under a constant load, and the shape slowly morphs. Now, this is usually reversible creep, meaning that if you could take the force off, the load off, then it would bounce back to shape. Elastic strain. But there's also some irreversible creep where basically small cement particles inside the concrete move. Now, this is a real big problem with bridge beams, and I'll show this to you in the next slide. So here we can see a bridge that's been built. Now, unfortunately, when they designed the bridge or when they constructed the bridge, I don't know if it was the constructor's fault or the designer's fault, you will find that actually this concrete that was used for this bridge has a lower modulus of elasticity than what is needed, meaning the concrete is a little bit too flexy. Look right there. Do you see the bridge beam there, how it sort of dips down? It doesn't follow a straight line. They didn't make the concrete like that. They didn't make a curved beam. What's happening there is actually, with all of the weight of the road and with trucks driving over it, the concrete is flexing. It's bending. And that's permanent because there's a permanent load on top of the bridge. This is what creep is. And it's an undesirable thing because potentially, first off, it's unsightly, but potentially if you had too much creep, those bridge beams wouldn't sit next to one another and you would end up with a big hole in the bridge. So it's a very common issue with bridge beams, but it's also a big issue with buildings. I live on a building which has 14 floors to it. Now, if the concrete used for the columns of the building has a low modulus of elasticity, then potentially I could measure the height of each floor, and I could probably find that the floor on the 14th floor will actually be a millimeter taller in height from floor to ceiling than the ground floor. Now, why is that? Because obviously they've designed all of the floors, ground to ceiling, that distance the same. Well, at the ground floor, it's got all of the weight being from all the floors above it, squeezing and compressing the columns holding the building up. Now, what that's going to mean is that there's going to be some elastic deformation and those columns are going to be squeezed. And it's very small, as I said. It probably doesn't matter for a building like this. It might be 5 millimeters or less. But any more than that, and suddenly components are not going to align. You're going to have windows that don't fit into the wall parts that don't actually meet the ceiling, and so forth and so forth. You need all of the components to fit firmly together. So creep is something that we need to be aware of, and that's one of the reasons why modulus of elasticity is important to us. So how do we minimize creep? Well, we do that by making sure that the modulus of elasticity is high enough. It can't be lower than about 20-30 GPa. Well, how can we do that? Well, first off, we can ensure that there's a high aggregate to cement ratio. That will mean it will be more resistant to creep. Remember, aggregate is less squeezable and less elastic than cement is. Also, if you have a high water to cement ratio, that's going to lead to more creep too and more elasticity. Why is that? Well, remember, if you have excess water, that's going to evaporate in time and you're going to have tiny microscopic air voids inside the concrete. Much like a sponge, how a sponge can be squeezed because it's mostly air, so air pockets inside the concrete can actually give it more elasticity. And another thing which is interesting, and I'm not really too sure why this is, and I'm not even too sure if we actually know. There's probably more research that needs to be done here. But rounded aggregates, as well as flaky aggregates, creep more than crushed angular aggregates. And what we think there is actually that with rounded aggregates, you tend to basically have a lower aggregate to cement ratio generally, because basically the aggregate particles don't interlock and form a tighter matrix as well as if they were crushed rock. So that can lead to a slightly higher level of creep. Well, guys, that's all I want to cover for today. Please join me for the next lecture, where we will be talking about strength in terms of durability and also shrinkage, that term we talked about a little bit when we studied cements. Thank you and goodbye.